Welcome to the fourth lesson on simultaneous games. In this lesson, I'm going to talk about the fundamental theorem of game theory, which is more commonly known as the Minimax Theorem. The Minimax Theorem states that every finite, zero-sum, two-person game has an optimal mixed strategy. By finite, we mean the number of strategies for the players. It was proved by John von Neumann in 1928. Minimax is another way of viewing solutions to games. For every two-person zero-sum game with finitely many strategies, there exists a value nu, the Greek letter, and a mixed strategy for each player such that, given player 2's strategy, the best possible payoff for player 1 is nu, and given player 1's strategy, the best possible payoff for player 2 is negative nu. Further, for two-player zero-sum games, the minimax maximin optimal strategy is the same as the Nash equilibrium. So we'll go through some examples to further clarify these definitions. On this slide, I'm going to talk about the algorithm or procedure for finding the minimax and maximin values, which I've highlighted here in bold. And they're complementary, although you're not going to come up with the same value typically. So determination of maximin strategy, we'll do that one first. In this approach, each player determines the minimum possible payoff for each of its possible strategies, and then identifies the maximum out of the minimum payoffs. There could be ties. The maximin value is the highest value, the maximum, that the player can be sure to get without knowing the actions of the other players. Equivalently, it is the lowest value the other players can force the player to receive when they know the player's actions. Then we have this complementary approach here, the mini-max strategy. In this approach, each player determines the maximum possible payoff for each combination of its opponent's strategies, and then identifies the minimum out of the maximum payoffs. There could be ties again. The minimax value of a player is the smallest value that the other players can force the player to receive without knowing the player's actions. Equivalently, it is the largest value the player can be sure to get when they know, they meaning the player, know the actions of the other players. For each player, the maximin payoff value is less than or equal to the minimax payoff value. We'll see this in an example. This approach can be used for non-zero sum as well as zero-sum games. I have an example here concerning our maximin concept. We'll do the mini-max on the next slide for the same game. So player 1 has three strategies, player 2 has 2 strategies. And we start by looking at what's the minimum player 1 can get for each strategy. So for strategy A, the minimum would be 2, right? It's either 3 or 2. Then 5 minus 11, so the min is minus 11. Then a minimum here would be minus 99, and we list those here. And then we take the max out of the minimums. That's the 2 that I have highlighted in green. Then we do the same thing for player 2. Player 2 plays X, the minimum would be a minus 3, and if the player 2 plays Y, the minimum could be a minus 33. So again, we take the max here, and that would be minus 3 out of these two. So for this game, the maximin optimal strategy is AX. In other words, we have the X being selected by 2 and A being selected by player 1. And so this 3-1 is the maximin optimal strategy in this particular game. If player 1 uses strategy A, it cannot do any worse than a payoff of 2. right? We saw that here. And if player 2 uses strategy X, it cannot do any worse than -3. So let's continue with this on the next slide. Okay, so now we do the minimax concept. You notice we've shifted here. We have player 2 listed in this column as opposed to player 1 that we had in the last slide, and player 1 listed along here. So just to warn you, it's not a mistake. So given each possible strategy for player 2, determine the maximum possible payoff for player 1. So when player 2 plays X, the maximum that 1 could get is 5. When player 2 plays Y, the maximum would be 4 for player 1. And then we take the minimum of these two max, so that would be 4. Then we do the second step here. Given each strategy for player A, determine the max payoff for 2. So if player 1 plays A, the max for 2 would be 1. If player 1 plays B, the max for 2 would be 3. And if player 1 plays C, the max would be 4. So again, we take the minimum of these maxes, we get 1. So for this game, the minimax optimal solution is AY, right? It's here and here, so it's 2 minus 33. If player 2 employs strategy Y, player 1 cannot do any better than a payoff of 4. And if player 1 employs strategy A, player 2 cannot do any better than 1. And the Nash equilibrium is CY. I didn't go through the analysis. You might want to do it as an exercise, but that's this one here, this cell here, 4, 4. And that's neither the maximin, which was here, right, AX, excuse me, 3, 1, or nor the minimax, which was AY, 2 minus 33. Okay, so we have three different possibilities here in terms of solutions. We have the maximin, the minimax, and we have the Nash equilibrium. The three solutions from the previous slide indicate different strategic directions or desires. The maximin approach asks, what is the best payoff I, as a player, can guarantee for myself, regardless of what the other player or players do? It is a conservative or defensive approach. Then we have the minimax approach, and that asks, how much can I limit the other player's best possible payoff? And then we have the Nash equilibrium, and the Nash equilibrium is what strategy profile is stable in the sense that neither player would benefit from changing strategy alone from that equilibrium. Then I have a little bit of explanation relative to the example. I won't read through those. You may want to just pause the video, and if you want to let that think in a little bit more. But I have a summary paragraph at the end. Thus, maximin emphasizes security. Minimax emphasizes limiting the opponent. And Nash equilibrium emphasizes mutual best responses and stability. In general, non-zero sum games, the three criteria may lead to entirely different outcomes. We saw that in the example. In two-player zero-sum games, however, the maximin and minimax values coincide, and they also form a Nash equilibrium. There may be other Nash equilibriums in the game, but the maximin, minimax form coincide, and they form a Nash equilibrium. Just continuing with our example, I have them both of the analyses listed here at the bottom. So we've already done this work here. In general, the maximin payoff is always less than or equal to the minimax payoff for each player. And I'll give you a reference to a paper on this that has, I believe, a proof if you're interested in that. So in our example, the maximin payoff for player 1 is 2, and the minimax payoff is 4, so it's less. And then the maximin payoff for player 2 is -3, and the minimax payoff for player 2 is 1. So in each case, they're less than the maximin or less than the minimax. And that's always true, less than or equal to. It can be proven that for a finite number of strategies, zero-sum, two-person games, the minimax and maxi-min strategies coincide. I said it on the last page. And are a Nash equilibrium. I also said that on the last page. And if you're interested in a proof, see theorems 4.44 and 4.545 in the book Game Theory, reference 2. So I'll put reference 1 and 2 in the information to this video if you're interested. Further, the payoff of player 1 is the negative of the payoff for player 2. This is under this condition here, not for this. This is not a zero-sum game. So the payoff for player 1 is a negative payoff for player 2 at the Nash equilibrium. So in two-player zero-sum games, the concept of Nash equilibrium, which is based on stability, and the concept of minimax and maxi-min coincide, but with the caveat you could have other Nash equilibriums other than the one from the minimax maxi-min. As I just mentioned, in a two-player zero-sum game, the concepts of Nash equilibrium and minimax maxi-min coincide. And I'll use this example to illustrate that. So first we do an analysis of best responses. So we see if player 2 plays X, then player 1 would play 3, so we put a little star there. And if player 2 plays Y, player 1 would do better to play 1. If player 1 plays A, player 2 has a better option playing X, we put a star there. And when player 1 plays B, player 2 does better with strategy Y. So we have the stars here. We notice there's no 2 stars in any cell. So there's no pure strategy, Nash equilibrium. So the next step is we look for a mixed strategy Nash equilibrium. So as we did in the previous lesson, we use the same technique here. We'll let sigma sub 1 be the probabilities for the player 1 playing A and B. So player 1 will play A with probability P, and probability B was, and play strategy B, excuse me, was probability 1 minus P. And then we have a similar setup for player 2 using probabilities Q and 1 minus Q for strategies X and Y. The requirement for sigma sub 1 is that when used by player 1, player 2 has no preference between going with strategy X or Y. In other words, they have the same payoff. So if we do the payoffs for player 2 based on playing strategy X, we have 2 times P, that's the probability player 1 plays A, minus 3 times 1 minus P. And then that needs to equal the payoff here. So it would be minus 1 times P plus 0 times 1 minus P. And if you do the algebra, you'll find that P equals 1/2. So our probabilities for mixed strategy, sigma sub 1 is 1/2, 1/2. Then the requirement for sigma sub 2 is that when used by player 2, player 1 has no preference between A or B. So then we see that here, if just looking at the payoff for A, using strategy A, it's -2 times Q, probability that player 2 plays X, plus 1 minus Q times 1. And then the payoff for player 1 using B, when player 2 uses the sigma sub 2, is 3 times Q plus 0 times 1 minus Q. And again, if you go through the calculations, you get Q equals 1/6. So our second mixed strategy has probabilities 1/6 and 5/6. Again, that applies to player 2 playing X or Y. Playing X was 1/6 probability and playing Y was 5/6. So let's continue on the next slide. Let's continue with the example. I copied the game down here at the bottom, but I've added the two mixed strategies. Remember, this was 1/2, 1/2 probabilities for playing A and B, and then sigma sub 2 was 1/6, 5/6 for playing X and Y. So I'm not going to compute every one of these. I'll just do a few. Since we've done an example of this before, it's the same idea. So for example, consider the case where player 2 utilizes strategy X and player 1 utilizes sigma sub 1. So here and here. And we want to compute the payoffs. So it's 1/2 times -2 plus 1/2 times 3. And that gives us 1/2. That's this number here. And then we need to compute the payoff for 2. So it's 1/2 times 2 plus 1/2 times -3, and that gives us a -1/2. Then it's even easier here. It's just 1/2 times 1 plus 0, and 1/2 times -1 plus 0. You get a -1/2. Let's do one of them going this way. If player 1 utilizes strategy A and player 2 utilizes strategy sigma sub 2, then we have 1/6 times -2 plus 5/6 times 1, and that gives us 3/6, which equals 1/2. That's this entry here. Then for the payoff for player 2, it's 1/6 times 2 plus 5/6 times -1, so we get a -3/6 or -1/2. Then we can do that here. This is, again, I guess I'm doing them all now, at least verbally. So this is 3 times 1/6. We're just adding 0, so it's 1/2, and then -3 times 1/6, and we get -1/2 since we're adding 0 again. And then using the shortcut we described in the last lesson, we just carry over this 1/2, 1/2, 1/2, because we're just taking a percentage of this and a percentage of this, and the percentage equals 100%, so you're just going to get 1/2. And then you do the same thing here, and we have our solution written out in detail. We need to continue on with the analysis on the next slide concerning the minimax and Nash equilibrium. So let's do that. Let's continue with our example. On this slide, I want to do the maximin analysis, and on the next slide, we'll do the minimax analysis. You notice here I've added the row and column so we can list the various minimums. So for player 1, if player 1 plays A, the minimum would be -2. If player 1 plays B, the minimum is 0. And if player 1 plays the mixed strategy sigma sub 1, it's 1/2 in all cases. So we get 1/2. Then we do the same thing for player 2. If player 2 plays X, the min is -3. If player 2 plays Y, the min is -1. And if player 2 plays sigma sub 2, it's -1/2 in every case. And then we take the max of the minimum, so that would be 1/2 for player 1, and the max of the minimums for player 2, and that would be -1/2. And then the maximin solution would be here, basically the two mixed strategies. And what I also did on this slide was the analysis for the Nash equilibrium, which turns out to be this here. We can go through it quickly. So for player 1, if we look across and we see what is the best for player 1, if player 2 plays X, and that would be 3. And if player 2 plays Y, the best for player 1 would be 1, so we put a star there. And if player 2 plays sigma sub 2, then all these are the same, basically 1/2, so we put a star next to all these. And then we look across for player 2. Player 1 plays A. The best solution is, or the best payoff is 2 for player 2. If player 1 plays B, the best payoff is 0. And if player 1 plays the mixed strategy sigma sub 1, the best for player 2 is -1/2, -1/2. So we put a star next to all these. And then we have a star next to this cell, both entries in this cell here. And so this is our Nash equilibrium, and it's also our maximin solution. So we've kind of verified, I guess, in one example, the general statement I made earlier. We still need to look at the Minimax solution on the next slide, which is very similar. So we'll carry over this, and then we'll just do the different analysis along the row and column here. I moved our table from the previous slide here, except for the bottom row and the right-hand column, because now we're going to compute the maximums and then take the min out of those. So for player 1, if player 2 plays X, the max that player 1 can get is 3. That's here. If player 2 plays Y, the max for 1 would be 1. And if player 2 plays the mixed strategy sigma sub 2, it's 1/2 in every case. Then we can do the same thing for player 2. If player 1 plays A, the best player 2 can do is 2. If player 1 plays B, the best player 2 can do is 0. And then if player 1 plays the mixed strategy sigma sub 1, player 2 doesn't care. It's he or she or it's going to get a -1/2. So we put that here. And then we take the minimum of the maxes, so that would be 1/2, and -1/2. You notice how these are on the other slide. This was +1/2 and -1/2. And again, the minimax solution is in this cell here, and it's also the Nash equilibrium. The same analysis we did on the previous slide applies here. I just left the stars in place. So we see that the minimax and maximin solutions point to the same cell here, basically using the the two mixed strategies, which happen to be, not just happen to be, it has to be a Nash equilibrium. Okay, so it's quite an involved theorem, but it goes over a lot of things we've done over the past several lessons. So you may want to scroll back in the video and view this a second time just to take in all the details. Okay, so I have one more example on the next slide. That'll be the final slide for this lesson. This is the last slide in the lesson, on simultaneous games. I'll have a few more lessons, at least one more, on sequential games after this lesson. In this slide, I want to show the possibility of having an infinite number of Nash equilibria, and I'll make use of this game here at the bottom to show that. We have two players. They each have two pure strategies. These are the payoffs. And if you do the Nash equilibrium analysis, you see that Bx and Ay, so this cell here and this cell here, are both Nash equilibria. What we want to do is create another strategy, a mixed strategy for player 2, and show that this particular combination A sigma sub 2 allows for an infinite number of Nash equilibria. So to do that, we'll have this sigma sub 2 defined by the probabilities P and 1 minus P. So in other words, player 2 plays X was probability P and Y was probability 1 minus P. And in that case, when player 1 plays A, the payoff for player 2 under playing sigma sub 2 is 3 times P plus 3 times 1 minus P, and that's 3. And the payoff for player A is 2 times P plus 5 times 1 minus P, and that's 5 minus 3P. And then we can compute the payoffs when player 1 plays B and player 2 plays sigma sub 2, and that's here. You notice they're both the same because it's just 3, 3, 1, 1, so you'd have 3 times P plus 1 times 1 minus P, and that's 2P plus 1. And if we do the Nash equilibrium analysis here, you notice that for player 2, when player 1 plays A, it doesn't matter whether player 2 plays X, Y, or sigma sub 2 because you get he or she or it gets a 3 in that case. So we would put a star next to 3. And in the case of player 1, A would be the better choice whenever 5 minus 3P is greater than 2P plus 1. And that happens whenever P is less than 4/5, and there's an infinite number of cases where P is less than 4/5, greater than 0. And so this combination, A sigma sub 2, is a max equilibria whenever P is between 0 and 4/5, and that happens an infinite number of times. Okay, so that was our final example in this lesson, and if you like this lesson, please give it a thumbs up and stay tuned for additional lessons.